All right, in 4.5, what we're going to get into is kind of an interesting topic in my opinion. There are different log rules. And what I mean by log rules are different rules that allow you to manipulate expressions that involve logs. So the closest parallel that I can draw for you are our exponent rules. Maybe you remember these from a few videos ago where I said we have these three exponent rules, 1, 2, and 3, and then there were three consequences that came from these rules. And then I added some additional statements like this statement here. And I said, really, this is just another way of viewing this first exponent rule along with one of the consequences. So I numbered them 1, 2, 3, but really you could argue there were, I don't know, 5 or 8, depending on what you wanted to find as a rule. At any rate, we had all these different exponent rules. It turns out there's things very similar, except instead of dealing with exponents, they deal with logs. So in this video, I'm going to derive 3 different log rules, and they'll kind of come from this statement, and this statement. So our second exponent rule here will actually never be used for deriving these log rules. I just wrote it kind of for completeness. And really, you don't need to know where these rules come from. I mean, you can kind of think about what I'm about to do as sort of proving these log rules or deriving them from these facts. I think it's really interesting if you think you might be a math major or go into calculus. It's a good idea to see this kind of stuff. But really, for the sake of a Math 112 class, all you need to know are what these 3 rules are and how to use them. And so in this video, if you just want to skip to the end and copy down these 3 rules, that's fine. You can jump to the next video where we actually do examples. Everything going forward, you can kind of consider optional. So our first log rule deals with anytime you're taking the log of something times something else, a product of numbers. It turns out that that's equal to the sum of 2 different logs. And you can go in 2 different directions here. So for example, if I asked you the log base 6 of 4 plus the log base 6 of 9, I don't think you know either of these values. I don't think there's any easy way to figure out what the log base 6 of 4 is, nor can you figure out the log base 6 of 9. I don't think you can figure out any power that you can raise 6 up to make it equal to 9. And I know it's tempting to think like, what about 1.5? Now, 6 times 1.5 is 9, but 6 to the 1.5 power is not 9. At any rate, I don't think that we know what this number is, nor do we know what this number is, but you could figure out the sum of these 2 things if you knew this first log rule. This first log rule says that if you have a sum of 2 different logs, that's equal to the log of the product of their different arguments. In other words, just take the 4 and the 9 and multiply them together and figure out what the log base 6 of 36 is equal to. 4 times 9 gives me this 36. And the log base 6 of 36, that's super easy, right? 6 to the second power is 36. What I'm saying is this answer is 2. Even though you couldn't have figured out this, nor could you have figured out this, you could figure out the sum of those 2 things if you had this first log rule. At any rate, the purpose of this video was less to give examples, I'm going to do that in the next video, and more to prove why this statement is true. And the way you prove it is kind of interesting. What you do is you start out with the log base b of x, and you give that a name. So I don't know, maybe we'll call it m. And then you get the log base b of y, and you give that a name. You call it n. And the reason you want to give these 2 things names is because what we're going to do is take advantage of what we know about exponent rules to come up with these log rules. So if I give these things names, now I have equations, and with log equations, I can rewrite them as exponential equations. If the log base b of x equals m, that means b to the m power is equal to x. And similarly, b to the n power is equal to y. And if b to the m equals x and b to the n equals y, well then x times y must be b to the m times b to the n, right? This is the same as this is the same as this, so this times this is the same as this times this. Why is this beneficial? Well, because now I can use this first exponent rule. Because note that what I have on the right side of the equation are 2 different exponents with the same base. And this first exponent rule says that anytime you're in that situation, all you got to do is add up those exponents. So x times y is also equal to b to the m plus n. That's the key step right there, right? Changing this line into this line using this first exponent rule is how I'm going to come up with this statement. I'm actually really close to this statement, even if you don't see it right now. All I have to do now is rewrite this exponential equation into logarithmic form. And if you're really good with the stuff we learned in logs in previous sections, that's no big deal. You're like, oh, the base is b, so I can say the log base b of the stuff on the other side of the equation, x times y, must be equal to whatever the exponent is, m plus n. And remember, m and n are the names that we gave for log base b of x and log base b of y. So what I've just shown is the log base b of x times y is the same as the log base b of x plus the log base b of y. This is exactly the statement that I was going for up here with my first log rule. I think that that's kind of interesting. I don't know if you're into proofs or if you're at all interested by this, that's good because when you get into some higher level math classes, this is the kind of stuff that you end up doing. And proofs are very different than solving equations like this. In my experience, a lot of times with the equations, somebody gives you a couple equations and you should be able to solve them. But with proofs, it's not that you should have been able to come up with this on your own at all. Even when you get into a higher level math class, you often can't come up with these things on your own. It's more, can you read somebody else's work and understand it? Can you kind of see what's going on here? Can you see how in this step we used this first exponent rule? And that equivalence is really what gave us this log rule to begin with. Wait, but how did you know to set log base b of x equal to m and log base b of y equal to n and then change that into exponential form? I didn't know how to do that. I read it online. It's kind of the same idea. That's what you should do. Don't hold yourself to the standard where you should be able to come up with these on your own, but see if you can kind of follow them. Oh, I see how this is the same as this, and this is the same as this, so therefore this equals this. See if you can follow each line individually. The second log rule is almost identical to the first log rule in terms of how you come up with it. What we deal with now is not the log of a product, x times y, but instead the log of a quotient, x divided by y. And instead of that being equal to log base b of x plus the log base b of y, it turns out that that's equal to the log base b of x minus the log base b of y. And maybe that's not altogether surprising. If you look at your exponent rules here, multiplication kind of changed into addition, loosely speaking, with exponents. And here I have multiplication changing to addition with logs. And here division changes into subtraction, loosely speaking. And here division is changing into subtraction. So maybe it's not shocking when you see this rule right here. I could come up with an example kind of like this to prove the need for such a rule. I could ask you what the log base 2 of 6 minus the log base 2 of 3 is equal to. And you'd be like, I have no idea because I don't know the log base 2 of 6, nor do I know the log base 2 of 3. And I'd be like, aha, you got this rule here though. And what you have is something equivalent to the right-hand side of this equation. So if you believe this log rule, you can rewrite this as the log base 2 of whatever 6 divided by 3 is equal to. And 6 divided by 3 is just equal to 2. So this is just the log base 2 of 2, which is just 1 because the power I got to raise this 2 up to make it equal to 2 is just 1. Again, I'm not supposed to be focusing on examples in this video. I'm supposed to be focusing on proofs. So what I'm going to do is something almost identical to this. I'm going to do that same trick where I name the log base b of x and the log base b of y, m and n respectively, just like I did here, because that will allow me to write this in exponent form, b to the m equals x, and b to the n equals y. And the reason I want to write it in exponent form is because I want to come up with something that I can use this exponent rule on, loosely speaking, to go between division and subtraction. So last time after I named these guys, I multiplied them together. I did x times y. Maybe it would make sense in this case to do x divided by y. X divided by y would be b to the m power divided by b to the n power, right? If this is the same as this, and this is the same as this over this is the same as this over this. But wait, b to the m over b to the n, isn't there kind of a rule for that? When I have the same base and I'm dividing two exponents, I can just subtract the numbers that are up in those exponents? Yeah, absolutely. So couldn't I rewrite this as b to the m minus n power? Yep, you sure could. Now what you have is an equation written in exponential notation. You could rewrite this in log notation by saying the log base b for this base of this x divided by y is equal to this exponent m minus n. And if you recognize that m and n are this and this respectively, instead of saying this minus this, I can say log base b of x minus the log base b of y. And what I get is the log base b of a quotient is equal to the difference in those two logs, which is exactly the statement here that I have for my second log rule. Third log rule, instead of using this exponent rule or this exponent rule, it's going to use this third exponent rule right here, but it's going to kind of follow the same beats that we used to prove the other two. What this one talks about is, what if you have the log base b of x raised up to some exponent? Well, it turns out that that's just equal to whatever the exponent is times the log base b of x. So how could this be useful? Well, imagine if somebody asked you, what is the log base 2 of 8 to the 100th power? And you're like, whoa, I got no idea because I don't know what 8 to the 100th power is. 8 times itself 100 times? That's going to get some huge number. My calculator couldn't even figure out what that number is without using scientific notation or something. But that's okay. This third log rule just says that this is the same as 100 times the log base 2 of 8. And the log base 2 of 8 is just equal to 3 because 2 to the third power equals 8. So this is just equal to 300. Even without knowing what 8 to the 100th power is, I can figure out the log base 2 of that absurdly large number is equal to 300. Sorry, those kind of all bled into each other. Again, I'm not supposed to be focusing on examples. That's for the next video. What I want to do in this video is prove this fact. And the way we're going to do it is we're going to kind of do the same trick we've been doing over here. We're going to start out with the log base b of x, and we're going to give that a name. M seems like as good a name as any. And then what we're going to do is we're going to rewrite this logarithmic equation into exponential form. B to the m power is equal to x. And again, the reason we're doing that, not that you should see this, is because we want to use exponent rules. So we have to get this out of log form and into exponent form so that we can use those rules. Now what we're going to do is we're going to say if b to the m power is the same as x, then b to the m power raised up to the t power is the same as x raised up to the t power. And even if you don't see why you would do that, hopefully you can at least follow that you could do that, that if this is the same as this raised up to some power like t is the same as this raised up to some power like t. That gets me this far. The advantage of this form is I can now use my third log rule here. I have an exponent raised up to another exponent, b to the m to the t. My third exponent rule tells me all I gotta do is multiply together those two exponents, m times t. This is b to the m times t power that's equal to x to the t power. This is a little bit confusing because I got lots of exponents going on right now, but I can rewrite this in logarithmic form using this base. I could say the log base b for this base of whatever's on the other side of this equation, in this case x to the t power, must be equal to this exponent m times t. Maybe instead of writing it as m times t, I'll write it as t times m, because multiplication is commutative, like 7 times 3 is the same as 3 times 7. I'm going to write it in this order just so things turn out prettier later on. What I have on the left-hand side here, the log base b of x to the t power, looks a lot like what I have right here. And what I have on the right side is t times m, but remember, m is just the log base b of x. So I can replace this m right here with the log base b of x. And that finishes the proof that the log base b of something raised up to a power is equal to that power times the log base b of x. I think these proofs are kind of fun. If you followed any of it, consider that bonus for a Math 112 class. Really, all you need for a Math 112 class are these 3 statements right here and the ability to use those 3 statements, which is stuff we'll develop in the next video.